The last section of chapter 1 is about inverse functions. And an inverse function, it basically undoes a function, and we notate that as f with that -1 as in the place of an exponent of x. So this reads inverse of f of x. Now, it's to note that it's not actually a -1 exponent, meaning we can't just say, oh, this is 1 over f of x to the positive first power. They are not the same. Oops, not the same. So if we have this set of ordered pair, 1, 5, 2, 4, 3, 3, and 4, 7, the inverse switches x and y. So the inverse would be 5, 1, 4, 2, 3, 3, and 7, 4. So like I said, essentially we are just switching the x and y values. Because we are switching the x and y values, the domain of f becomes the range of the inverse, and the range of the original becomes the domain of the inverse. You can verify that two functions are inverses of each other by doing the composition. We talked a little bit about compositions the other day. So if you show that both compositions are true, f of the inverse of f is equal to x, and that the composition of the inverse of f of x with f of x is also x. So what that means is f of the inverse of x has to equal x, and when you compose the inverse with f of x, you must also get x. So to understand some relationships with inverses, we're going to look at f of x equals x squared. So if we were to look at a table for f of x equals x squared, we have an x and y, 2, 3, 4, and we just use our basic 5 points. 0. So that would be f of x, and we'll just draw a rough sketch of this. And plot these points. Okay, so we have f of x. Now the inverse, remember the inverse is when we change x and y. So if we were to start a new table, we have x, and then we have the inverse of f of x. Okay. And we switch the x and y values. So we have 4, 1, 0, 1, 4, -2, -1, 0, 1, 2. So I just looked at my table above in pink and switched the x and y values. And then let's go over and plot those points. So you see a couple of things. It kind of looked like this thing is shifted. And if you look at our table, you'll notice that, oh, we have x values that repeat. So this can't be a function because x values are repeated. So the inverse of f of x is not a function because x values are repeated. Remember we said that y values can repeat, but x's can't. And we had that vertical line test to tell us if a graph is a function. And if we go and look at our pink graph also fails the vertical line test. So we can also say that f of the inverse of x, or inverse f of x, is not a function because it fails the vertical line test, VLT. Now we can also do what's something called to the horizontal line test to the original function, or in the original graph, to tell us if the inverse is also a function. So if we were to draw a horizontal line through the original, we see that we touch 2 times. Well, that will tell us that when we do the inverse, that the inverse will fail the vertical line test. So we can perform the horizontal line test on the original to determine if the inverse is a function or not. So functions that are called 1, 2, 1 have inverses that is also a function. So what 1-to-1 means is that each y value is related to only one x values. So no y values or x values are repeated if its function is 1-to-1. And to write this down, the horizontal line test is used to see, or used on the original. Let's write that part to emphasize on the original function to determine if the inverse is a function. Now, if a function is 1-to-1, then the inverse will also be a function. And like I said, 1-to-1 means that there's no x values or y values being repeated. So our y equals x squared up here, our y values are repeated, which tells us that this is not 1-to-1. So the inverse will not be a function. On the next page, we're going to talk about how to find inverses algebraically. So we're going to use a horizontal line test to determine whether the inverse is a function. The domain may need to be restricted for the inverse to exist, and we'll talk about those. We're going to replace f of x with y, switch x and y, and then solve for y, and then replace it with the inverse notation, and then include any domain and if any restrictions on the domain if necessary. So it's sometimes a good idea to figure out the domain and range first of the original, because then we can switch that to get the domain and range of the inverse. So this one, f of x equals 5x minus 7, that's a linear function. And a linear function passes the horizontal line test. So the domain of this will be -infinity, infinity. The range is also -infinity, infinity. And when we talk about the inverse and we switch them, the domain and range, they'll still be -infinity, infinity. All right, so we have y equals 5x minus 7. We will switch where x and y are. Just switch locations. You're not taking the coefficients or anything like that. Then we're going to add 7 to both sides. We get x plus 7 equals 5y. Then divide everything by 5. That's going to give us 1/5 x plus 7 over 5 equals y. We now have y by itself, so we're going to write this in inverse notation. So you'll notice that inverses of linear functions are also functions. We don't need to do any restrictions or anything like that. All right, so now this one, we have f of x equals the square root of x minus 2 plus 1. So the domain of this, and it might help to look at a rough sketch of this function. It's a square root function, and we know it looks like that because there's no reflection or anything. And this point is 2 comma 1. So the domain of this original function is going to be positive 2 comma infinity, and the range will be positive 1 comma infinity. So that's the domain and range of the original, which means the domain of the inverse will be 1 comma infinity. All right, so we're going to write y equals x minus 2, the square root of x minus 2 plus 1. Switch where x and y are. Okay, so then we'll subtract 1 from both sides. X minus 1 equals the square root of y minus 2. Then we'll square both sides. When we square both sides, this will give us x minus 1 squared equals y minus 2. Now we don't need to multiply out x minus 1 squared. There's nothing in the problem to suggest that we need to. So then we add 2 to both sides, we get x minus 1 squared plus 2 equals y. All right, y is by itself. So then we have the inverse of f of x is equal to x minus 1 squared plus 2. Now the domain of this, if you weren't talking about inverses, you say, oh, that's a quadratic. The domain is negative infinity comma infinity. But the range up here, when we were talking about the original function, was negative 1 comma infinity, which means the domain of this is also, positive 1 comma infinity. So this would be our answer because we have to restrict the domain since the range was not negative infinity comma infinity. So that's going to be probably one of the more difficult things is to remember when you're talking about the domain of our inverses, we have to look at the range of the original. So now with these problems down here, what we're going to do is we're going to restrict the domain of the original function so that the function is one-to-one and has an inverse that's also a function. Then we're going to find the inverse function, state the domain and ranges of f and the inverse. So if we look at this absolute value graph, just to kind of draw what we have, our vertex is at positive 1 comma negative 2. And because our a value is negative, we have a negative out in front, our graph looks like this. Well, this fails the horizontal line test, so we want to restrict this domain to only deal with one part of this v. And we always want to deal with the positive, or the part going to the right. So we are only concerned about this part right here. Because now if we're only concerned about this part, our function becomes one-to-one, and our inverse will also be a function. So we have y equals negative absolute value of x minus 1 minus 2. And we know that the domain of this original function, because we restricted it, our domain is 1 comma infinity, and our range is negative infinity, comma 2. Now, I know that may be confusing because we would say, oh, the domain of absolute value is negative infinity, comma infinity. But because we're trying to make this one-to-one, we have to restrict it. And the easiest way to determine how to restrict these is to draw a picture like this. And so now we're going to switch x and y. All right, minus 2. And now we have to get y by itself. So we'll add 2 to both sides. We have x minus 2, or sorry, x plus 2 equals negative absolute value of y minus 1. And then we have to get the absolute value bars by themselves, so we'll divide by negative 1. So we get negative x minus 2 equals the absolute value of y minus 1. Now remember, in absolute value equations, we would split it up right here and solve two separate ones. But because we restricted the domain of the original, we only care about positive, because our original domain goes from 1 to positive infinity. So we don't need two separate equations. So we're going to have negative x minus 2 equals y minus 1. Add 1 to both sides. We get negative x minus 1 equals y. So then our inverse is going to be negative x minus y. And the domain is going to be the range of the original one, 2 comma negative infinity, comma 2. And the range is going to be 1 comma infinity. So it is a little bit of a complicated process to get our restrictions settled. All right, so then this one, our last problem, it's a quadratic. So let's kind of, again, get an idea of what this looks like. Our vertex is at negative 3 comma 1. So we know that this fails the horizontal line test, which means we have to restrict our domain. So we're going to, again, restrict it to the positive side. So then our domain, once we restrict it, is going to be negative 3 comma infinity. And our range is going to be positive 1 comma infinity. Right, so now let's calculate the inverse. Y equals 2 times x plus 3 squared plus 1. We'll switch our x and y. So x equals 2 times y plus 3 squared plus 1. Subtract 1, x minus 1 equals 2 times y plus 3 squared. And when we divide both sides by 2, we get x minus 1 over 2 equals y plus 3 squared. So when we square root both sides right now, it's going to get a little bit messy. So we get y plus 3 equals the square root of x minus 1 over 2. And we know we can't have a square root in the denominator, so we have to multiply the top and bottom by the square root of 2. So the numerator, so we have y plus 3 equals the square root of 2 times x minus 1 over 2. And then when we subtract 3 from both sides, we need to make sure that we don't accidentally put that minus 3 underneath the square root. So yeah, that is an ugly looking inverse. So our final answer is going to be the inverse of f of x is equal to the square root of 2 times x minus 1 over 2 minus 3. Our domain was the range of the restrictions we made up here. So our domain is 1, comma, infinity, and then our range will be the domain of what we had up here, negative 3, comma, infinity. Right, so things are starting to get a little intense with these last couple problems. So if you need to rewatch it, do so, ask questions. But I think you'll get it. We're just combining a bunch of stuff that we've been doing this chapter. So thanks for watching. Make sure to like the video and subscribe.